All right, here we go. 6, number 3. We've got mass 2, we've got mass 1, and we got a pulley of a mass with R1 and R2. So the key to this one is realizing that they've given us a pulley with some thickness. So when we look up our moment of inertia of that pulley, it's not going to be a straight hoop or a straight disc. It's going to be the thick-walled cylinder. And we'll have to look that equation up on our cheat sheet or derive it. So what do we got here? Basic situation is they're both moving at the instant we start carrying about. So we've got a velocity here initial. We have the same initial velocity here, which means our pulley is rotating with some moment or some angular velocity as well. So what kind of energy do we have going on? Because the problem in this one in part A is how fast are the blocks going after they've slid a certain distance, and how fast is the pulley spinning after that same distance. So this is an energy problem, excuse me, because they're asking about a final velocity. They're not asking about time or acceleration. They're just asking about how fast are these things going. So total energy approach here. We got the kinetic energy of this thing, kinetic energy of this thing, kinetic energy of this thing, and then we've got the gravitational potential energy that's driving the whole system, causing the system to accelerate. So we've got this gravitational potential energy from M1 that's going to cause the whole system to gain some total energy or some total kinetic energy. So here we go. So with all energy approaches, we're going to start out with the initial amount of energy minus any work from friction or plus any work from external forces. That's positive work. Here we've only got friction doing a thing, so we're going to have negative work from friction, and then we're going to have a final amount of energy. So what kind of energy do we have in this question? Well, block 1 is moving, so it's got kinetic energy. Block 2 is moving, it's got kinetic energy. The pulley is spinning, it's got rotational kinetic energy, and block 1 has the potential to fall, so it has some gravitational potential energy. So there's your 4 energy storage mechanisms to start with. So we got 1/2 m1 v1 squared, 1/2 m2 v2 squared, and 1/2 I omega squared, plus m1 g delta, what did I call it there? Delta H, okay? So that's all your initial amounts of energy. The tricks here are making sure you're using the right moment of inertia formula for the thick cylinder of the pulley. So 1/2 mass of the pulley, R1, which is the small radius squared, plus R2, which is the biggest radius squared. Look that up on your cheat sheet if you need to realize that that pulley's got a thickness. It's not a thin hoop and it's not a full disc. So that is the formula for our thick-walled cylinder. And then converting the angular speed of the pulley into the linear speed of the blocks by using our translation equation. So the initial velocity over R2, and important here, this one's R2 because the string is wrapped around the larger radius, which they've called R2. So hopefully that makes sense. And then the potential energy that's going to get converted into the extra kinetic energy the system's going to have by speeding up, but also we're going to have to take away that work from friction. So there's our initial energy setup. Boom. Hopefully you got that down. We'll go over the work from friction. All right. Work from friction is pretty straightforward. It's just your kinetic frictional force times your delta x in this case. So you got your mu normal and then you got your delta x. In this case, your delta x, the distance m2 slides, is the same as your delta h, the distance that m1 falls. So whatever number you got for that, I got 0.7. Doesn't really matter. But your delta x sliding distance is the same as your delta h falling distance in your equations. So there's your negative work from friction. You got your coefficient, which is given. You got your m2, because it's m2 that's sliding on the surface. G, of course, you get the normal force. And then your delta x, which is the distance it slides across the surface. Okay, so then your final amount of energy is all kinetic, right? We're going to say that that block has fallen to its lowest point, and M1 no longer has any gravitational potential. So all the energy in this system is just kinetic, of course, after subtracting out that work from friction. So M1's moving, M2's moving, and the pulley's spinning. Again, the moment inertia is the same as before, so same equation before, and converting your angular speed to your linear speed is the same also as before, using your R2, the larger radius where the string is wrapped around. So that's pretty much it. You just got to put those three parts together. Your initial energy minus your work from friction is equal to your final energy. This problem gives you numbers, so then you just got to put in all your numbers and hopefully get the right number. Email me your questions. Like and subscribe.